So, how's everyone doing? Mixed reactions, that's fair. So, I haven't said enough lately. Test week starts today, specifically this afternoon. And as such, my main focus for all of lecture this week is to address any questions and concerns you guys have, namely any questions you encountered while you were studying. So, what's in your minds?
Do we have to do this?
Do you have to take the test?
Yeah.
I mean, to pass the course, you have to have a grade for it. Technically, you could not take it, in which case the highest you could get in the course would be an 81.
That's a little deep.
Right. That's not bad. That's not bad.
Yeah, but you have to get 100 on literally everything else, including the final and test 2.
You can get 100 on the final.
It's possible. Like, I give bonus points on it too.
Did you say we can like draw on it and you like give us points?
Mm-hmm.
See?
If you got a 0 on this test, you could still get an 81 on the class if you aced literally everything else. But it's in your best interest to show up and at least write something down so that you get more than 0 points for it, for test 1. Does that sound fair?
Yeah.
Because if you get more than 0 points, your highest score is higher than 81, right? Math is
The math
mathing.
is math.
Is it? Like, is the math mathing for you guys?
I just wish we like knew like our scores even on the lab, especially with Edwards.
Oh, well, he actually sent them to me. So as long as you've been attending lab, which I have here the sheet of everyone who's been attending, then your lab average is currently 100. Question?
What percentage of our grade is like the lab portion?
17? Hold on. I have 2 slightly different rubrics for all of my different courses, so I need to pull up this course's syllabus real fast.
I could like get a 40. Like literally pass.
I got to finish the homework.
Cause I didn't bomb. Give it 0.
Course
It's
info,
not 81.
2013 syllabus.
And isn't
Bless you.
it?
For this course, lab is 17% of your grade, which is as important as, almost as important as a single test. So coming to labs every week is basically the 3rd test.
So if you bomb a test and get 100s on the lab, you're still good.
Yes. Again, this is all weighted in such a way that no one thing will ever kill your score in here, not even the final, if I'm being honest. What did someone say?
What if I fail the final? What would my grade be?
Okay, well, what constitutes a failed final to you?
Like a 50.
Okay, a 50. If you got a 50 on the final, your score could top out at an 85.
Dang.
I'm good.
I'll do better than 50.
My version goes.
Yeah.
Is it final cumulative?
Yes.
Of course
No
it is.
trick question.
Well, I mean, it's cumulative to the whole course, and the whole course has included 3 questions.
Just take them out.
Okay, let's see.
Wait, are there gonna be chairs?
The second half of the class will have noticeably less trig because after we finish this first test, chapter 6 is going to be about momentum and collisions. Chapter 7 will be about rotation. And we're going to start getting into things like sound and energy. Sound, waves, sorry, not energy. So there'll be less trig moving forwards, which means that the cumulative, test 2 actually might not have any trig on it. The final though will, because it's cumulative including test 1, but it'd be like proportionately less trig for every point on the exam, if that makes sense. Like if the final is the whole semester and test 1 is like 30% trig, the exam would be like 15% trig.
Test 1 is 30% trick.
But I don't have that number, that's just a sample number.
I would say that's pretty accurate. 30 to 40%.
Probably. I can give a quick cursory glance.
Is it?
Please. Okay, this one might be closer to 50%, right?
Yeah. Oh my god. 70%.
Not 70.
I don't even know how to do this.
Okay, 50% of test one questions involve trig to some degree. Is it? Okay, you're allowed to decide what you're outraged about. That's not a function of my expectations. So if it's an outrage to you, then it's an outrage. Please file complaints in my new office.
We'll be back to you in 2 to 3 business weeks.
Yes.
So when I was studying, I noticed that when you're doing the questions where it's the pulley and there's 2 different weights, I might have missed this, I guess, in class, but is the force of gravity no longer M times G? Is it gonna be the weight of the box?
Well, M times G is the weight of the box. So are you talking about on the practice test?
Yeah, I think there was one like that on the practice test.
Now let me pull up.
That makes sense though, because that would be the weight.
Okay. I can get my answer key in a sec, but this is the file I'll pull up first. So here, this doesn't give the mass of each box. This gives the weight of each box. Note that it's written in newtons. So these are the weights, Fg, and you would actually need to, as a part of this process, use the weights to find mass, since you need the oops. Since you do need the mass, so you do still have to use this, but in this specific case, you were told weight, and you need to calculate mass from it. So always notice whether it says weight or mass, and then separately what the unit is. Okay. Yes.
Alright, so on the homework for the online, I was struggling with the problem where there was a box on each side connected, and I was having trouble trying to get the tension of the strings. How would you do that?
Well, that and this are similar questions, but let's look at the homework one first.
I think it's chapter 4, question 8.
All right.
No, I didn't,
Oh wait, chapter 4, question 8 is 3 boxes. Is that the one you're looking at?
Yeah, where there's one attached on each side.
Okay, you did say that, sorry. All right. So, in this particular question, there is going to be 2 tensions that you have to find, and that is because there is 2 different ropes. Each single rope has its own single tension, but there is 2 ropes here, one tied to the left and the other tied to the right. So for each of these 3 boxes, I would recommend examining all the forces present on each single one. There's 3 of them, so I'm going to look at net force 3 separate times. And I just got this marker. No, that's fair. That's what this room's for. So net force 1. So looking at the forces on the first box, and really all the forces present on box 1 act in the y-axis. We'll have tension up and its own weight downwards. And that's going to equal its mass times its resulting acceleration. Said acceleration will point down, so I'm going to make that a negative. We'll elaborate on that in a second. Next is box 2, and it's moving in the x-axis, so we'll look at its x-axis forces. Within the x-axis for box number 2, tension 1 is pulling it to the left, which would actually make it negative. Tension 2 is pulling it to the right. What direction do you think this system is going to start moving?
The left.
The left, very good. This box is the most massive one, so if this thing moves, that's going to cause everything to shift in this direction. So M1 will descend, M3 will ascend, and M2 is going to slide to the left. That determines the direction that friction will act on M2. Because if friction moves to the left, what direction is friction going to point on it?
To the right.
To the right, very good. And that means, the way that I'm setting this up, force, friction, kinetic will actually be positive, pointing in the same direction as T2. And all three of these x-axis forces will add up to its mass times its acceleration. And if left is negative, then its acceleration will also point in a negative direction. Lastly, all the forces on object 3, which are also in the y. Object 3 has it T2 up. Again, this rope. This is all one rope, but it's all distinct from this one rope. So, first object has T1 pulling up, second object has T1 to the left and T2 to the right, third object has T2 up. And its own weight down. And that will add up to its mass times its resulting acceleration, which will point up, and that's a positive direction. So these are the foundations of your three formulas, which contain three separate unknowns, T1, T2, and A. Since they're all tied together, they'll have the same acceleration. We just have to take care of the fact that two of these A's point negative and one points positive. Question?
So just to make sure, like, if M2 wasn't there and you just had the two boxes on either side, you could just erase the middle one and like use the same formula, right?
Yep.
Okay.
Yeah, if there was no M2 and it was just one rope all the way across, this wouldn't exist. And within your remaining two equations, it'd be the same tension across both of them because it's one rope in that scenario. So adding that third box kind of exponentially complicates things, unfortunately. How's that feel for the starting point?
It's the start.
It's a start. Now, in terms of actually doing this as a homework question, first it says draw a diagram, and WebAssign can't grade this. You can upload anything and get a free point. So, whatever image or Word doc you happen to have on your laptop, upload it, you get a free point. It's not going to actually grade it. You should still think about these force diagrams and probably draw them yourself, but you're not going to get graded for them because, again, WebAssign isn't advanced enough to analyze images like that. So the actual things you are being asked for, first, determine the magnitude and direction of each object's acceleration. We've already talked about what direction they will all accelerate in, and they will all have the same magnitude of acceleration because they are all attached. So most times every time we have done a question like this, every object that is tied together shares an acceleration. And that's why it's the same A, even if it's negative, in all three of those equations over there. They all share an acceleration even though their masses are different. And we've also been asked for what is the tension in each of the two ropes. And that kind of, again, brings us to a 3 equations, 3 unknowns sort of scenario. The 3 unknowns being T1, T2, and A. And as long as you have the same number of equations and the same number of unknowns, you can combine all these together to find eventually all 3 of them. What I'd recommend doing for this one is solving this equation for T2, this equation for T1, plug those results into the second equation to find the unified A. And once you have that acceleration, you can pop it back into the other 2 to find the different corresponding tensions. So same basic process as the one we did in class where there was only 2, just slightly longer. Yes.
Can you go over question 5 on the practice test?
Yes. Load up the file that has answers on it. So, practice test question 5 is a tension and vector addition type of question. But there's also net force involved, because here we have a 10 kilogram flower pot being suspended by 2 ropes. Both ropes are at 60-degree angles, but they're on opposite sides, and so they're kind of mirrored from one another. And what we've been asked to do here is to find the tension within each rope. So, kind of similarly, I would recommend thinking about the net force present on this flower pot. But we're looking at the net forces on one object, and we should examine both the X and the Y, since there are both X and Y forces present on the flower pot. In the X-axis, you would have the X component of the 2 tensions opposing each other. And for this entire question, the net force is going to be 0, Y.
There's no acceleration.
There's no acceleration. If you want to hold something still, the acceleration needs to be 0. Therefore, all the net forces all the forces present need to add up to a net force of 0. That is the entire baseline premise of holding something in place. Net force equals 0, therefore acceleration equals 0. And immediately, this actually tells us something very useful. The X components of the 2 ropes are the same. They oppose each other perfectly and cancel out, and that's why the pot doesn't move in either X direction, left or right. Looking at the Y-axis, there's actually 3 Y forces present, those being the Y components of the 2 tensions, and also the weight of the flower pot, but they must again all add up to 0. Again, for pretty much any question that involves multiple forces acting on an object, it is worth using this as a starting point. 1, it lets you analyze how many forces are present and how they all must add together. And 2, it's a useful reminder of what the net forces should be adding up to. Either 0 if it's not accelerating, or MA if it is accelerating. Whoever asked about this one, questions thus far?
No, it's good so far.
Okay. Now, currently, we don't have numbers for the X and Y components of the 2 tensions yet. So, next step would be doing a little bit of trig to divide T1 and T2 up into its components. We don't have a number for T1 or T2, but we can at least turn it into the form of sine 60 equals ty1 over t1, therefore t1y equals t1 times the sine of 60. We don't know what t1 is, but we know what sine of 60 is. And if we do this to all of them, we can make them all in terms of the two unknown tensions rather than just their legs. So if we do this to both of t1's legs, we get the y leg is t1 times sine of 60, and the x leg is t1 times the cosine of 60. And frankly, t2's end up being pretty much the same because it's the same angle for the other row. The only real difference would be that the x leg of t2 points in the opposite direction as the x leg of t1, just based on the mirrored, the mirroring of the row. And when we plug this information into our net force formulas tells us, we already kind of determined that the x legs must be equal and opposite, because if two things add up to 0, they must be equal and opposite. And the two x legs, one of them is t1 cos 60, the other is t2 cos 60. And so if you set them against each other, t2 cos 60 equals t1 cos 60, the cos 60 just kind of cancel, and the two tensions, whatever they are, must be the same thing. Which kind of makes sense. The ropes are mirror images of each other. It makes sense that the tensions would match. We just don't have a number for them yet. But we've proven that the two tensions should be the same, meaning that all the way down the rest of this question, we don't have to differentiate between T1 and T2 anymore. We can just find one T, because they're the same thing. So when I did my work for the next part, the y-axis, after plugging in the y legs, which are each respective tension times sine of 60, I didn't bother differentiating T1 and T2 anymore, because they're the same thing. I just wrote T from that point on, and solved eventually for the one unified T of 56.6 repeating. No, it's not repeating, never mind. Now the tensions will only match here because of it being a mirror image. That won't always happen, but it's worth taking that into account and thinking about what that means for this question in particular.
So in that bottom equation, would the sine 60s also cancel each other out like in the previous one?
Not exactly, because over here we wound up like we had two things with cos 60s adding up to 0. So if you send one to the other side, you get a cos 60 on both sides. In this version, the next step would look something like t sine 60 plus t sine 60 equals 98, because here we get 10, here we have the weight of the flower pot, it's mass of 10 times negative 9.8. So originally it was t sine 60 plus t sine 60 minus 98. Send the 98 over and that makes it positive on the other side. And right now we don't have a sine 60 on both sides, they're both on one side. And so what I did was I just literally added them. 2 times t times sine of 60 equals 98. And so rather than cancel it out, we just divide it over, divide by sine 60, divide by 2, and that should land you at t equals 56.6.
And then if they're like not equal to each other, then you would just have to do all of that twice, basically.
Yes.
Like you'd have to just do one for each side.
Right, if they weren't the same, like if the angles didn't match, for instance, if the angles were just two different things, then likely the two equations here would end up giving you a two equations, two unknowns scenario. And technically it did, it's just one of them told us the two things equal each other. This was technically two equations, two unknowns. It's just, I don't know, a less annoying version? one of the equations just happened to simplify to one equaling the other, and we technically plugged that into the second. So, unique take on the concept. Good. Any other questions about this one for right now? Okay. What else is on your minds? Yes.
For question 3 on the practice test, I did like a different equation, but I didn't get like the same answer, so I was just a little bit.
So you did something else and got a different answer.
Yeah.
Okay, I asked what the different thing was.
Yeah, at first I did like the t equals the square root of, I think it was g times 8, or it was t equals the square root of height times 2 divided by gravity to
Right.
find time, and then I plugged that into that same equation. But I'm thinking like that my mistake was like getting t.
Right. What happened there was that form, which, did you get that from lab? Okay, I remember Dr. Edwards using that version. That worked if you were launching sideways, and that means that your initial vertical velocity is 0. So that formula he was using is technically a simplified form of the quadratic. Because within this quadratic, the b terms are the initial velocities. Then we had 4 times half of g times height, and then over g again. So that would simplify down into the version that he had on the board there, which sounds like made it into your notes. So this is the more, like, using the quadratic is generally the better answer. That simplified equation assumes initial vertical velocity is 0, which is not actually true here. Here it is launching at an angle both out and upwards. And the presence of a non-zero initial velocity kind of necessitates the use of a quadratic.
Okay, thank you.
Well, yes.
Would we ever be asked, like, if we found, like, if the acceleration, like, was going in a pulley system to find, like, how much they move?
Mm-hmm. Wait, like the distance they move?
Yeah.
Hmm. That is a great question. Let me. I want to be as non-vague and as helpful as possible. So, looking at the test I have written, that scenario does not come up.
That's good then. Just making sure.
Now in general though, if you know acceleration, you can find displacement using like formula 3 or 4. But again, that's not going to be on this test.
Do we have to find acceleration?
For a pulley system?
Yeah.
You are all allowed to hear that. The answer is no. Sorry, I'm being coy and I don't know. I'm being pointlessly coy. Yes.
Can we do number 8 on the practice test?
Yes. Good question. Because the ramp pictures are interesting. So here we have a box sitting on a 30-degree slope. First question is, draw a free body diagram of every force present as this thing sits absolutely still on this ramp. Now, as long as we're on planet Earth, we're going to have gravity. So that's one of the three forces that are here. Next, if you are sitting on a surface, there will be a normal force, but remember that normal force is always perpendicular to the surface creating it. Flat surfaces point perpendicularly up, but slanted surfaces point out. And in that case, that means normal force is going to be tilted this time around. There is also a second tilted force because friction is always parallel to the surface creating it. And if this box is being held in place, then there must be some force of friction opposing the motion it would want to do. Like it would want to slide down the ramp, but friction says don't do that. It must point opposite the attempted motion. And so rather than some motion happening parallel down the slope, friction would have to point parallel up the slope. So there are three forces here, then that's a general rule. If something is being held in place on an incline by friction, then these are the three forces that would act on it. Gravity down, normal force out, friction parallel to the ramp. So first question, well, the answer to the first question here is these are the three forces, these are the direction they point if something is being held by friction on a slope. Frankly, even if it's moving on a slope, this would be basically the answer. It would just be kinetic friction instead of static friction.
Does it matter which side you put the friction on, like for kinetic and static? Is that different?
The friction should always oppose motion. So technically you could draw this arrow over here, but it should still point opposite the motion. So the arrow should always point opposite the motion. Does that answer the question? Okay. Now part B asks, what is the force of friction holding the box in place? And this triangle is something you can draw on your formula sheet, because this is the relationship between all three of these forces present here. I promise you this triangle works. It's just it took me like a year of physics as a major to be able to just recite this from memory. You're allowed to write it down. The reason I found it weird as a student is I always had a hard time remembering where this 30-degree angle went. Because in my own head, like, it always belonged somewhere else at first until it finally clicked with me like a year into my major's program. I guarantee you, the angle of the slope is the same as the angle between normal force and gravity. And that's technically true on flat surfaces as well. Because on a flat surface, which is a 0-degree incline, the angle between normal force and gravity is 0 degrees, because they're parallel. On a very slight incline, so a very shallow angle, the angle between normal force and gravity is also very slight. And then on a very steep incline, so like almost 90 degrees, gravity still points down, normal force is going to point almost horizontally, and that's kind of why normal force vanishes on a, if you're like, if I hold this here, there's no normal force to keep it in place anymore, because at 90 degrees it just vanishes. So if I drag this over, very big angle between normal force and gravity. Again, you get to a certain 90-degree point and normal force just goes away. So the angle of the slope is also the angle between normal force and gravity. Draw that picture on your formula sheet. Because it took me a year to be able to do that from memory. I don't expect you to suddenly do it from memory either. The other thing to note about this triangle is gravity is the hypotenuse, because the normal force leg is automatically perpendicular to whatever force is parallel to the slope by virtue of normal force being perpendicular to the slope. So whatever form of friction is acting, or possibly any other force in that axis, normal force is automatically perpendicular to it. And that means that the right angle has to live here, making gravity the automatic hypotenuse. Because the hypotenuse is always opposite the 90 degrees. Using that triangle, we can actually use trig to solve for the force of friction. Since if you know the mass of the box, you can find the weight of the box, and therefore sine of 30 is opposite over hypotenuse. Sine of 30 would be friction over gravity. Plug in the weight, plug in sine 30, we can find the force of friction, and then use the friction formula properly to calculate what the mu would need to be to hold the box in place. It'd be a little bit more trig to find a number for normal force, though. I forget who asked, how does this feel? Can I ask, can you vocalize what feels about it?
It's just like a matter of seeing it and understanding where the angle falls in the triangle and understanding how to make the triangle.
That's fair. So I'm just trying to think of how to, like, what tips I can say, or how differently I can phrase it. Technically, all three of these vectors are the same and point in the same direction as this picture. How does this picture feel? Okay. Does the presence of each force and how they act in this scenario make sense? All right. All three of those need to be there if you are sitting on an incline. Gravity, because we're on planet Earth. Normal force, because the incline is always going to press out of itself. And really, these two forces combined are the reason why objects tend to slide down ramps. Because if we ignore friction for a sec, like say this was a frictionless surface, and these were the only two forces present, this one would point straight down, this one points up and left. Adding these together would give you a force down the ramp. So the addition of these two things is why things slide down ramps. If I can actually, let me make the arrow a little closer to actual size. Gravity points very strongly straight down. Normal force points less strongly both left and up. The up and the down only partially cancel out, because gravity is bigger than the vertical component of normal force, since normal force gets weaker as you slant, and it's going to get weaker until it just vanishes at 90 degrees. So as the ramp increases, normal force constantly gets weaker, which means its vertical component is constantly decreasing and therefore doing a progressively worse job of fighting gravity. So then also gravity can't do anything about the leftward pointing component of normal force. For that reason, these two by themselves add up to something that points down the ramp, and that's why objects tend to slide down parallel the length of the ramp. So ignoring friction for a second, the interaction of these two things is why things slide down ramps. These two would add up to a net force pointing this way. When friction is present, though, it wants to oppose this motion, and that's why the friction points that way, at a right angle to normal force. this marker's dying too. So that's where these three vectors come from on this diagram. And then getting from here to here is mainly a function of just taking those arrows and dragging them into the shape of a triangle. Because they all point in this, the way that I drew this, I know that the whole thing is not drawn like a standard right triangle where you got one leg horizontally, one leg vertically, and the hypotenuse is on a slant. The reason that it's tilted like this is I just kept every single vector here in the same orientation and dragged them into a triangle shape. Gravity still points straight down. Normal force still points up and to the left. Friction points up and to the right. Yes?
So like with that, like on the free body diagram, I also had like written like that the F, like FG is also like equal to like two lines kind of going like out of it and doing like mg times mg cosine whatever the angle is. Cause like since gravity won't be like in a straight line.
Well, gravity is in a straight line. Oh, hold on. May I look at your notes?
Yeah. Like since gravity kind of comes like this way, I don't know if that's relevant for the test, but I just wanted to understand.
It's,
Because then like to find like the acceleration, I'd have to like do all the stations together.
okay, so that A would be along the slope. All right, so that would work if you were asked for acceleration. That is a slightly different tactic where A is along the slope, and that means that you can kind of, there's a certain train of thought. Since A points this way, rather than like figure out the XY components of A, you can just kind of tilt the perspective of the question and make A your new x-axis. In which case, gravity now points at a weird position and has XY components. So that work is dividing gravity up into the components so that the components are in the same axes as normal force and force down the ramp.
Okay, but on the test run, I'm not gonna have to find acceleration then.
No.
Okay.
In the interest of honesty and for simplicity's sake, you're not gonna have to find the acceleration down the slope of a box sitting on a ramp. The one question that is relevant to that, the box is sitting still, therefore there is no acceleration, therefore all the forces add up to zero. Welcome. Which actually makes it very similar to this question. All the forces here add up to zero, the box stays in place, therefore every force present forms this triangle. You asked about this one originally. How does it feel?
Better.
Better is good. I like better. How's everyone else feeling? Any other questions, needs, concerns right now?
Are we allowed to like take a break during our test, like a 5-minute break, like if we do half of it and then take a break during this?
Yes. Now, well, so you have 3 hours to take a 1-hour test.
Yeah.
Now, I would consider taking a break to be like setting the test aside for a second, maybe just stopping to breathe and close your eyes. I wouldn't say pull your phone out. But you can definitely just pause, go to the bathroom, get some more water, You have 3 hours to take a 1 hour test. It's designed to take 1 hour. You have up to 3 just for the benefit of your own sanity and also academic accommodations. So yes, you can just stop. You can sit and do nothing for a while. Does that answer the question?
Yeah.
Okay. You have until 4:30. I find honestly most students just kind of hit a point where more time doesn't really help because they've done everything they can. Yes.
Here's a question.
How many conceptual questions will be on the test, and then like conversions?
There's officially 2 concept questions, which is to say there's 2 questions that should not require any numbers. And one of them is, again, identifying the laws of motion, which I've said probably 8 million times, but you do have to identify the laws of motion. So that's 2 questions that don't require any calculating. The other 7 are designed to take calculations, but I still grade them for like interpreting your conceptual understanding, like using the correct formulas, making good drawings of physically representing what's going on, drawing in, like dividing vectors up into their components, things like that. And so even if all you write for a given question is technically math, I'm still looking at it for conceptual understanding. And additionally, if it's technically a math-oriented question and you are just stumped, first of all, ask the proctor, because we want to make sure that you understand what's being asked of you. Make sure you know what the question is actually about. But even if after that you've been staring at it and you're still stumped, write a paragraph about the concepts involved. Like say you get to a question like this, and you don't, like this math is just not coming to you, you can write a paragraph about how you know what forces are present, maybe that you know normal force tilts at an angle even if you don't quite know what to do with it, and I will give you points for those concepts. So you can turn math questions into concept questions. Like you have to do math to get an A+, but you can still, I will still give you points for all of the things that aren't math that you do put down. So 2 questions that don't require any math, 7 questions that I want there to be math for, but technically you can earn points for anything you write, including paragraphs about concepts, or sentences about concepts. It doesn't have to be paragraph form. You also get points for just writing formulas down. Like, say you get to projectile motion. Just writing down this formula once is gold. Because if you write this down, you indicate to me that you know something is accelerating and displacing over time. And this is a very important formula here because you end up using it twice, once for x, once for y. So writing down related formulas is instant points. Making drawings is instant points. And again, if you're blanking on math, writing out just sentences describing concepts like how gravity works here, like how you know it's going to move in 2 axes at once, just more points. Write down anything you can think of. I'm wanting math, but I will give you points for things that aren't math. I've given points for a drawing of Yoda before. It's not a good answer, but it's an answer. So, let me know if you need anything. You are also allowed to take the test during any of the 4 slots. It doesn't have to be your normal one. You can take it later if you want to study. You can take it today if you just want it over with. That's up to you. Let me know if you need anything. Have a great day.